Next, we are going to look at correlation. We all, from our daily lives, have an intuitive understanding of what correlations are. What you see on screen is a toy dataset with information on 32 cars that was extracted way back in 1974. It has 10 key attributes relating to every car: how many miles per gallon, how many cylinders does the car have, what is the engine size or displacement, and so on. And we know that several of these variables are highly correlated with each other, whether positively or negatively, they are connected. And we will see these results in a moment. So, for example, if we were to consider weight and miles per gallon, we would expect them to have an inverse relationship, or we would expect them to have a negative correlation, because as weight goes up, we would expect the miles per gallon to reduce. And that is exactly what we see here. Our correlation measurement is minus 0.87. And again, we also know from high school math that correlations vary between minus 1 and plus 1. Minus 1 means a perfectly negative correlation, plus 1 means a perfectly positive correlation, and 0 means no correlation at all. So that's what correlation is about. Again, we can also look at another variable here, calculate correlations. So if we were to consider the correlation between uh, the engine size and weight, or displacement and weight, we expect them to be positively correlated. The larger the engine size, the greater would be the weight of the car. And we see that in a correlation value of 0.89 here. Now, what we saw here was the Pearson's correlation coefficient. Now, that's not the only game in town. There are many ways to calculate correlation, though Pearson's correlation coefficient is the most commonly used uh, measure that you would find. And when people talk about correlation, that is what they are normally referring to. Now, here is a more uh, technical definition of how the correlation calculation works, but we are not going to go into that. We don't need to, because as managers, leaders, and as people who are trying to apply analytics to profit from data related situations, the math is less important. So the good thing about Pearson's correlation is that it neatly varies between minus 1 and plus 1, and it allows for an easy human interpretation. And examining correlations between variables is really a part of just about every analysis you would be doing. So you have a data set, you will be calculating the correlations between variables. And here is the formula for calculating correlation. It's really just the covariance divided by the product of the standard deviation. So it's normalized by dividing by the standard deviation. We talked about this already. Now, what are the limitations of Pearson's correlation coefficient? One challenge is that it assumes a linear relationship between variables. When the relationship is not linear, for example, where in a simple situation like this, we have a parabola that is a description of y equal to x squared, and we know that there is a very strong association between y and x. In fact, X completely and 100% accurately predicts Y. So we know that there is the association. But when we calculate a correlation, we get a value of near zero, which means that Pearson's correlation coefficient fails to detect this nonlinear relationship. Uh, so how do we deal with this limitation? That's a question. And an even bigger problem is that when we have categorical variables, and categorical variables are really just categories like gender, names of countries, um, species of animals that are not numbers, then Pearson's correlation coefficient cannot be calculated. It can only be calculated for numbers. So before we go in there, this is a good time for a quick digression into the types of data that we will run into. So we have continuous data, we have categorical data, and we have ordinal data, which is a type of uh, categorical data. So far, most of the data that we looked at, including for the diamonds data set, also for the cars data set, it appears as numbers. They can take any value. So this includes things such as price, your speed, temperature, engine size, and things such as those. And these are called continuous variables. But some variables, and as I mentioned, gender, species names, countries, etc., can only take certain values. These are called categorical variables. Sometimes these categories may have an inherent order to them. For example, education levels may have categories such as no high school, BS, MS, PhD, and so on. Or you may have scales that reflect high, medium, or low. Such variables are called ordinal variables, as there is some order to the categories. Calculating correlation becomes more tricky when the variables are not continuous. So if you have numerical continuous variables, it's easy to apply Pearson's formula and get a correlation estimate. But very often we run into variables that are not numbers. So how do you calculate a correlation? And more importantly, forget correlation, how do you establish if there is any association between those variables? Does one affect the other? That really is the question we are asking. So if you're looking at pay and gender, does gender and pay affect? Are these connected in any way? Or age and pay, are they connected in any way? So that is something that we can examine using other statistical techniques, and let's go through those at a very high level. So when variables are not continuous, how do you establish association when you can't easily calculate correlation? So there are methods that have been created to address this problem. When you are trying to compare a categorical variable to another categorical variable, then you do something called a chi-square test, which is a statistical technique to determine the association between two categorical variables. And we will look at it at a very high level in the next slide. When you are trying to compare a continuous variable to a categorical variable, then you do something called a one-way ANOVA. And we will look at that again at a very high level in a subsequent slide. So let's look at that. But before then, I also wanted to talk about a new correlation computation. It's called phi-k. It came out not very long ago. It's written as phi-k, the symbol that you see here, and that is available in both Python and R, and allows us to calculate correlations across all types of data. And that is something that we will be using, and I will be showing it to you as well. So as managers, as leaders, we are able to assess whether two things are correlated regardless of the type of variable that they are. And one good thing about phi-k is that it can also take into account complex nonlinear relationships. Just like we saw Pearson's correlation coefficient failing for a nonlinear relationship, that it does not happen with phi-k. One challenge though is phi-k varies between 0 and 1, not between -1 and +1. So while it tells us about the strength of the relationship, it doesn't tell us anything about the direction of the relationship. So that is something we will have to interpret ourselves. So let's look at categorical to categorical variables. How do you establish association between them? Now this is from a toy data set, some information on about 3,000 students, some of whom live in a dorm and others do not. And at the end of their graduation, some of them received a job offer and were placed, and some others were not. And what we want to know is there any correlation between living in a dorm and receiving a job placement? And we don't know the answer to that. All we have is this data here, and we have to think about are these two things connected? Maybe the dorm people get to study more. The people who don't live in a dorm, they have to commute and they spend a lot of time doing that, and they don't have the right environment to study, and therefore their placement rates are lower. One could intuitively argue the other way as well. Maybe the people who live in the dorm party too much and don't get a job placement at the end of their studies or at the end of their education. We can actually calculate percentages. So we can convert this table to percentages uh, as how many of the dorm people received a placement, and how many of the no dorm people received a placement, and we see that the numbers are 56% received a placement if they did not live in a dorm, and 52% received a placement when they did live in a dorm. So is this difference material, or is this just like a statistical quirk? Does it matter? And again, is there a way to figure this out? Now, if there were to be no impact between a student's living situation and their placement, we would expect things to be equally distributed between the cells, as in this table. So, really, what we did here was we took these numbers and we spread them out equally between the yes and no columns for placement. And this is what my ideal distribution would have looked like if there was no connection between the two. We can then compare this 970, which is the ideal, to what the actual was, the observed value 945, and try to do some calculations to understand whether there is a correlation between these two factors. And this is again done through the chi-square test, as I explained earlier. And I am not going to go into the math of this, but really the essence of this is that by comparing what we expect the distribution to be and what the observed distribution was, we can do statistical tests and identify whether there's a difference or not. And that is what this is about. In fact, in this case, there is not a difference between the two groups. Let's now look at continuous and categorical variables together. And remember, recall the diamonds data set that we looked at. So the diamonds, each diamond has what is called a cut, which is of 5 different types. So there are 5 different types of cuts here. Uh, and each one has a different average sale price. And the question is there a difference between these average sale prices? Does the cut actually impact the sale price of a diamond? And we can see that, well, the first two, yeah, there is a pretty big difference. But the next two, these two here, don't have a lot of difference between each other. And then what is the average sale price of all the diamonds taken together? And how do all of these numbers compare to that? And those are the questions that come to our mind. And that is exactly what the logic is intuitively that is applied as part of one-way ANOVA to understand if there is an association between these two variables. We can calculate the average price at which each of these categories sell, which is there in the table. And we would expect the average prices to be the same if cut did not affect uh, the selling price of the diamond. And we can actually calculate a box plot as well, which means that for every cut, we can see whether what the distribution of the data is like. We will be covering box plots later in the visualization video, but for the moment, understand that these are really just an explanation of how far your data is spread out from the minimum value to the maximum value, and these are the 3 quartiles. That's what these boxes represent. And when we do a one-way ANOVA test, we are able to find out that these actually are related. We are not going to perform the calculations here, but there is a way to do that. And the intuition behind that is that it looks at how the averages between the groups compare to each other and to the dispersion inside each of these groups. So that is what one-way ANOVA does, but that is not the topic for our discussion, and we will keep moving. The good thing for us is that all of this is encapsulated in the phi-k correlation calculations, which means that we are able to get this information done for us. All of this work is done for us, and we are able to calculate correlations between all kinds of variables. So here we have a correlation table. The intersection of two variables gives you the correlation between them. This is structured as a heat map, which is very nice because it allows us to visually spot any high correlations or low correlations pretty quickly without having to dive through an ocean of data. Now, obviously, because we have so many variables, we have a large number of correlations as well, but it gives us some sense of how the data is connected between each other. On this slide, what we have is we have two uh, comparative calculations of correlation. This that you see here is the phi-k based correlation calculations. This is the same as the one on the previous slide, except that this is in a different color. And what we have here is the Pearson's correlation calculations. These are the ones that vary between -1 and +1 and relate only to numbers. What you will notice is that the categorical variables are missing here. It only looks at numerical variables because that's the only one that it can be applied. Let's now think about analyzing distributions. How are distributions spread out? We all have worked with and know about percentiles and quartiles, and let's just very quickly revisit them because they're fairly straightforward. We use them every day and are intuitively understandable. When we calculate percentiles, we really divide our data into 100 different groups, and a certain percentile gives you how many scores in the frequency distribution fall above or below the score for that percentile. And that's a lot of words, and it is easy to get lost in that, but it becomes practical with a real example. Now, here is an example again from the Census Bureau. And what I would ask you to look at is the first line in the data, which is this here. So we have all of these different percentiles for income distribution in the United States in 2021. And this is the 10th percentile limit is 15,660. What that means is that 10% of US households make $15,660 a year or less, and 90% make more than that. In the same way, the 60th percentile limit is $89,744, and so on. And the 50th percentile, as you can imagine, is nothing but the median itself. The 90th percentile is $211,000. And uh, when we put it like this, then percentiles become a lot more easier to understand than the words that describe the measure. Quartiles, again, very similar to percentiles, except that they divide the data into four equal parts. So 25th, 50th, and 75th percentile are equivalent to the first quartile, second quartile, and the third quartile. The difference between the third and the first quartile is referred to as the interquartile range, or IQR. And this is again something we will look at when we do visualizations and when we look at box plots. Finally, the last thing in descriptive statistics that I wanted to cover was standardized scores, or z-scores. Z-score measures the relative location of a value in the dataset, and it helps us figure out how far a particular value is from the mean for that data set uh, and compared to the standard deviation for that data set. And really what it is you take the observed value, you subtract the mean from it, and you divide it by the standard deviation. And if you recall the discussion on standard deviation, most of your values are going to lie within 3 standard deviations of your mean, which means z-scores greater than uh, 3 on either side of the mean. So anything lower than -3 or anything greater than +3 would be quite unusual or abnormal. They could potentially indicate outliers. So this is also called the standardized value. This is a very useful computation that we often have to do, especially when we get to modeling. because many machine learning and deep learning algorithms, they're affected by large values, and it is important to convert data into normalized or standardized z-scores, and it's very helpful there. One other thing to know about z-scores is that when you convert data into a standardized value or a z-score, you're not losing any information. The information is still all in there, which means you can recompute the original value from your z-score. So you're not, they're informationally equivalent. That is one thing to keep in mind. And that brings us to an end to this discussion on descriptive analytics. Hope you enjoyed it. For those who are interested in the code, please do look at the coding video, and we will look at a Jupyter notebook where we will go through all of these things in detail as to how these are executed in Python. With the discussion on descriptive analytics completed, I wanted to take a minute to talk about the limitations of descriptive analytics. On screen, you see four different data sets. So this is data set 1, this is data set 2, this is 3, and this is data set 4. And you will see that they're all completely different. The first one is just random scatters of data. The next one has a pattern, a parabolic pattern. This one is a sort of a downward trending line. And here we have all of these things in a straight line, but an outlier sitting over here. So they're completely different in the way they are. However, the way these data points are constructed, if you were to calculate their descriptive statistics, you will find them to be completely identical. This data set is called Anscombe's quartet, named after the statistician who created them. And each one of these data sets has 11 data points, and the purpose why he created them, why Mr. Anscombe created them, is he wanted to counter the impression that numerical calculations are exact, but graphs are rough. When we graph the data, we see the differences between these distributions. And when we actually here, for each of these data sets, when we look at how what the descriptive statistics are like, they're listed here. You see that the count for all of them is the same, 11, and the mean is the same between x and y for each of them. Same thing for standard deviation, minimum, maximum, the different, uh, um, the, the percentiles are not identical, but the median is. And the correlations are also identical. It's interesting to see that. The correlation is 0.81 amongst all of these data sets, which is just fascinating to see. So I think it's a pretty interesting illustration of how descriptive analytics alone are not enough to summarize their data, and that's something to keep in mind. With that, I would like to thank you for watching this video. Thanks a lot, and see you in the next one.